Hello and welcome. This time, I'm going to implement a simple example using the USART peripheral of the ATF32 Microcontroller. As shown in this image, the project involves receiving a byte and retransmitting it, but increment by 1. Also, if the incoming byte equals 3, it turns on or activates an LED, and if it equals 7, it turns it off. The schematic diagram of the board shows that the connector labeled J8 has access to USART number 1, and that 1 will be used. Here I have the workbench, and the crystal and configuration pin settings are the same as previous projects, which I recommend checking out and leave in the description. What's new are the USART terminals, where for USART number 1, I've calibrated some parameters such as the baud rate, number of bits, parity type, and stop bit. For the data flow direction type, I have selected both transmission and reception. I have enabled the interrupt, as I want it to work this way, both for transmission and reception. The mode is obviously asynchronous, and hardware control is disabled. This means there are only the transmission and reception terminals. There are no lines called CTS and RTS. For this project, I need an asynchronous delay, and I don't want to use the system timer, which is only 24 bits. I will use timer 5, which can work with a 32-bit width. I recommend watching the asynchronous delay video that I will leave in the description. The plus mode option is the one that allows the timer to work with that bit width. I will operate at its maximum speed, so I set the prescaler option to 0. It will be an upcounting timer, the period will be at its maximum 32-bit value, and the frequency will be 240 MHz. Any other configuration is unnecessary. In the clock configuration, you can see that timer 5 is operating at the frequency I mentioned earlier. Also, I must remind you that, from now on, every project will use the Watchdog Timer. Refer to the video titled, Watchdog Timer and the ATF32 Microcontroller, from Artery Technology, for details about that timer. Here I have the generated code. For example, here is the line that configures timer 5, where it is set up in 32-bit mode and all parameters are calibrated from the workbench. And it seems that it is already enabled to function. There is also the watchdog function, which was explained in a previous video. These two lines were added by me. The first one initializes the watchdog, and I'll explain the second one later. In the main loop, I recalibrate the watchdog to prevent a CPU reset, and the next line is one I created. If I go to where it was created, you can see that I have a function, which is a task responsible for managing USART1. Similarly, if I refer to that function, you can see that it is a state machine, where each state executes a portion of the code, ensuring that there is never a complete appropriation of the CPU. In the first state of the task, I enable the USART receive interrupt and change the task state to the next one. In the second state of the task, nothing is done, it simply waits for the interrupt enabled in the first state. The function that is invoked by the receive interrupt is here, a little further up. In this function, it checks if the task is in the second state, which was mentioned earlier, where the task does nothing, or in the third state. If this condition is met, the received byte is stored in an array, which has a variable acting as a pointer that was initialized to 0. After storing the received byte, that pointer variable is incremented by 1 to store the next arriving byte in another position of the array. Next, it is verified that this variable has not exceeded 10. The reason is that if we look at how the array was declared, its size is 10 positions. So, going back to the task, if 10 bytes have arrived, we can assume that a complete frame has been received, and we must process that information. Otherwise, the task switches to the third state. This change occurs if it was in the idle or second state. If it was already in the third state, nothing happens, and a timer value is captured to generate an asynchronous delay. Here, there is an error. It's not timer 2, it's number 5. Next, I will explain the third state, related to reception. You can observe an asynchronous delay of 10 milliseconds. I recommend watching the video related to this type of delay, which I have linked in the description. If that delay is met, it can be assumed that no more bytes will arrive, as the received frame doesn't necessarily have to be exactly 10 bytes long. Once that delay has passed, the process moves to the fourth state, related to processing the information that has been received. Again, I correct the mistake. The timer used is 5, not 2. Returning to the function invoked by the reception interrupt, each time a byte arrives, the variable related to the asynchronous delay is updated with a new value. And in this way it can be said that the asynchronous delay is reinitialized. The else in the if statement would occur when a byte arrives while it is in another state not related to reception, for example, processing the information or transmitting. In such a case, I think it should be discarded, and this instruction that reads the arriving byte is intended to clear the USART reception buffer. It should be determined whether this step is correct or not. If not, it could be commented out. Now I will explain the fourth state of the task, related to information processing, which occurs if the asynchronous delay ends, or if 10 bytes have been received. If the first byte of the array is equal to 7, the LED diode is activated. If it is equal to 3, the LED diode is turned off. Then, the first byte that arrived is incremented by 1. In this for loop, the reception array is transferred to the transmission array, and the variable called number of bytes to transmit determines how many bytes will be transmitted. Remember that the variable acting as a pointer to the reception array also indicates how many bytes have arrived. After the for loop, there is also a variable that acts as a pointer for the transmission array, which is initialized to 0. Then I enable the interrupt when the USART transmission buffer is empty, which means that immediately after this line of code, that event will be triggered. Finally, I change the task to the fifth state, which also doesn't do anything. The task will exit that state when the transmission is complete. The transmission interrupt invokes a function that I named transmitByte, which is located a bit earlier in the code. In this function, the first thing it does is take a byte from the transmission array, pointed to by the pointer variable, and send it to the USART transmission buffer. This function is called each time the transmission of a byte is completed. Then, the pointer variable is incremented to transmit the next item in the array. If that pointer equals the number of bytes to be transmitted, we can assume that the entire data frame has been transmitted. If that happens, I disable the interrupt that signals the transmission buffer is empty, reset the received pointer to 0 for a new data reception, and finally change the task state to idle. This way, the task is ready to repeat the process. Something I should point out is that the task also has a function where you can initialize anything necessary, such as the task state and, in this case, resetting the reception pointer to 0. Regarding the asynchronous delay, I use a function that gets the absolute value of two 32-bit integers. Again, I recommend watching the video in the description to understand why this function is used. Returning to the main function, there was a function called sysinitialize, which I didn't explain what it does. If I navigate to where it is used, you can see that it invokes the function that initializes the task. What I still need to indicate is where the functions related to the USART1 receive and transmit interrupts are called from. If I go to the generated file, where all the functions related to the microcontroller's interrupts are located, in the one related to USART1, you can see that if the interrupt was due to reception, the function store received byte is invoked, or if it's because the transmission buffer is empty, transmit byte is invoked. That's the theory. Now comes the hardware test. Here is the hardware. You can see the previous project where pressing the user switch activates the green LED, and the program counter stays in an infinite loop until the Watchdog Timer resets it. At the top, on a prototype board also known as a protoboard, there is an RS-232 to USB converter, which is connected via wires to USART1 on connector J8. Before running the test, I'm going to make a change to when the data transmission starts. I'll place the task state change related to transmission before enabling the transmission interrupt. Upon analyzing this, I realize that when this interrupt is enabled, the related function is immediately invoked. If only one byte is transmitted, the task state will change to idle, waiting for a new reception. But when returning to line 98, it will switch back to the transmission-related state and will never exit that state. Alright, now I navigate to the debugging option and its properties, and I start a new debugging session. I wait until the software communicates with the debugger, and the program counter stops at the first line of code in the main function. A window pops up indicating that a new perspective needs to be opened for debugging, and I click on the option labeled Switch. Once the debugging stops at the first line, I press the button that allows the program to continue running. I use the software called Hercules to open a serial port, which is COM6 on my computer. The first number to send is 1. I send it, and you can see that the microcontroller returns 2. Now I send 3, and you can see that it returns 4, and the green LED on the board has turned on. Next, I send the number 4, and it returns 5. I send 7, it returns 8, and the LED turns off. I send 3 again to turn the LED back on. So, I can say that the project works as expected. Thanks for watching the video.